Hello, and what's up? Today, let's dive into how we can create compelling, detailed, and dynamic audio worlds using WwiserR's static sound emitters. As we've seen in the previous video, the static sound emitter component inherits from the sound emitter base, and, as such, exposes functions to post one-shot AK audio events and AK GameSynchs. On top, it can post static sound loops to the static sound emitter manager, which in turn will continuously cull all those posted sound loops, based on their user-defined rules, and post the necessary play and stop events on the corresponding emitters. Thanks to a spatial data structure known as Octree, and Unreal's multithreading, it can do this very efficiently even with hundreds of thousands or millions of sound loops being posted. To better understand how this works, let's first look at some examples from a designer's perspective, before taking a look under the hood of the static sound emitter manager. The WwiserR static sound loop is a data asset, in which the user can define a set of rules for distance culling the associated audio event. A fade-out time and curve can be set to smoothen out transitions when a playing audio event gets culled or stopped by the user. Next, we can set how many instances of this sound loop can play simultaneously. Indeed, we can see that only the 8 closest instances are now playing. As Benny desperately looks around for mushrooms, we notice that, as he gets closer to a group of trees, the majority of sounds is playing from a single direction. To achieve a more homogeneous sound field, we can limit the number of sounds that can play from a single direction or quadrant. To emphasize this effect, I'll disable the fade-outs for now. The static sound emitter manager is now selecting at most 2 sounds per quadrant, resulting in a much more balanced sound field. Now, let's go for a less aggressive setting, allowing 3 sound instances per quadrant, and enabling the fade-outs again. As you can hear and see, the resulting sound field is much more balanced and immersive. Although all of this works well to create a consistent sound field around our distance probe, which is attached to Benny, for sounds with a shorter attenuation range, such as the ferns, we might rather want to prioritize instances closer to the camera. Back in the static sound loop data asset, we can select any position between the listener and its distance probe that we want the static sound emitter manager to use as reference for this specific audio event. When we set this halfway between the listener and the probe, we can see that our focus on the ferns shifts to those in front of the camera. Let's add some different trees to our scene. We can either do this by using a different static sound loop for both tree types, in which case their audio events are culled independently. Or we can use the same static sound loop for both tree blueprints, and use a switch to select their specific type. In this case, they will be culled together. Surely, we can post GameSynchs just as on any sound emitter type. For example, the crickets in the first part of this video use a switch for evening versus morning, and an RTPC for picking 1 out of 6 possible cricket types. We could go even further. If we would, for example, have an elaborate weather system in our game, we could set corresponding RTPCs every tick. To only do this for sounds that are actually playing, and not ruin our game's performance, we can use the static sound emitters, on playing state changed event, to toggle the tick function accordingly. Finally, similar to posting audio events in the previous video, we can override the distance within which a sound loop should be considered by the culling system, to better reflect the actual audible range, and squeeze a bit of extra performance out of the CPU. It's also worth noting that, except for the AK audio event and activation range, all the static sound loop properties can be overridden at any point at runtime. Now, let's look at how the static sound emitter manager handles all of this blazingly fast. Each static sound emitter world manager maps any posted static sound loops to an octree containing all the emitters on which this static sound loop has been posted. Every frame, for each posted static sound loop, it checks which loops to start or stop playing, processing each static sound loop in parallel, as this is where the heavy lifting happens. In doing so, it honors the WwiserR optimization philosophy, correlating performance cost to what we hear in the game, rather than the size of the map, level, or project. It does so by first selecting all the emitters within the activation range, filtering the emitters that should be playing, using the rules set by the user in the corresponding static sound loop data asset, comparing those to the emitters that are already playing this loop at this point, and finally prompting the necessary emitters to either start or stop playing the respective audio event. To conclude this video, let's do some performance profiling and find out how fast our system really is. I'll first disable the viewport stats, to not add any noise to the measurement. Switching to Unreal Insights, we can see that the CPU load sits between 700 microseconds and 1 millisecond per frame. Since static sound loops typically are purely cosmetic, rather than time-sensitive gameplay sounds, we can safely introduce a couple of frames of latency, without this being noticeable to the player. As such, we can spread the culling process over multiple frames. Indeed, in the project settings, we can divide the static sound loops into as many distance ranges as we like. Let's set our range thresholds to 50 and 100 meters. I must admit that previously I've been slightly lying, as the posted loops are actually stored in an array of maps, where each element represents a distance range. As such, in our example, the static sound emitter world manager will process any static loops with an activation range shorter than 50 meters every first frame, between 50 and 100 meters every second frame, and larger than 100 meters every third frame, and so on. As a result of this optimization, the CPU load drops to between slightly under 300 and 600 microseconds per frame. Finally, to better understand the impact of dynamically posting and stopping static sound loops at runtime, I'll reduce the number of emitters to about 20,000. The CPU load now sits between 40 and 60 microseconds, when no static sound loops are being added to, or removed from the system, and goes up to at most 250 microseconds per frame when posting about 400 loops per second. And that's all for today. I hope you liked this video and got a bit wiser in the process. Thank you very much for watching.